with the great seminar from Maciej, who from the University of Warsaw, who's going to take it away right now.
Okay. Hi. Hi everyone. My name is Maciej Kierkla. I'm a PhD student from Warsaw. Today I'm going to talk about our recent paper, which landed on archive today before I landed on Nippon, which is us right there. And yes, we did the paper with my supervisor, Maciej Kierkla, and our collaborator, Alexandra Skaram from Estonia. So I'm going to talk about our results in a conformal extension of classically conformal extension of the standard model. We studied there the phase transition and the resulting gravitational wave signal, and also the dark matter within the model. So I'm going to focus mostly on the phase transition and gravitational wave part. So let me begin with a short description what a phase transition is. So you can imagine phase transition as the Higgs mechanism was a process that took place in the early universe. So when our field was here, everything that was interacting with this field was massless, and then it moved to the new phase, the broken or massive phase, and then particles began to have mass. Okay, and of course, such transition could have proceeded smoothly. However, this is indeed the case in the standard model alone. However, the more interesting case happen if we have this barrier there, right? And this can only happen in the beyond standard models. So in that case, the transition proceeds by the so-called bubble nucleation. So the bubbles with a new broken phase inside of them start to appear randomly in the whole universe, and they start to expand until they fill all of the universe, and the transition is finished. And as they expand, their collisions and interaction with plasma could be a source of gravitational waves, which we'll be able to observe in the future. And that would be a smoking gun for new physics beyond the standard model, because you have to have something more than standard model alone to have this kind of phase transition. Okay, so my supervisor always said that good talk should have a story. So here's mine, the table of contents. So chapter 1, we have to choose the DSM model. So we are choosing the classically conformal extension of the standard model. It's called SU2CSM. It consists of the standard model and additional SU2 gauge group. There's a new scalar field, which is a doublet under this new SU2, while singlet on the standard model. And those two sectors interact only by the Higgs particle term. And also there is a new gauge boson X, and this is our vector dark matter candidate. It's stable. It's fine. This C letter. So this means this classically scale invariant. And by that, I mean that there are no dimensionful parameters in the Lagrangian. We don't have this minus m mu squared term, right? And here you can see the 3-level Lagrangian of the theory. And okay, one may ask, but you need that term to generate the masses after all. So what do? So the solution comes is the so-called Coleman-Weinberg mechanism, or radiative symmetry breaking. So here's the example of a toy theory, massless electrodynamics. So I have scalar, I have one vector field, right? So on the 3-level, it looks like this, right? I just have the simplest potential for the scalar field, no symmetry breaking. But then, if I compute the one-loop quantum corrections, I have additional term, right? And this term allows me to generate this famous symmetry breaking form of the potential. And I can generate the masses, right? Okay, so this has some non-trivial consequences for the phase transition, especially because if we have, there's a key difference between this conformal kind of potential and polynomial. And well, you can see it basically here that conformal potential is flat in the beginning, while polynomial is going down more rapidly, faster. So because of that, phase transition can happen in this model significantly below electroweak scale. In the more detailed version would be much below the critical temperature when the two minima degenerate, but I will get to that. Okay, and this is due to the simple fact that how do we get the barrier? We get it from the thermal corrections, right? So in that conformal case, even the slightest correction will produce the barrier, and it will last till the t equals 0, right? In the polynomial, well, those corrections have to grow a little bit larger till we have the barrier. Okay, and that's how we can supercool to with the so the transition can take place in a low temperature. Also, because of that, there is a lot of energy stored in the there's a lot of energy released after the transition completes, and because of that, we can have generically a strong gravitational wave signal. Okay, but one have to be careful. So here is the pictures of the potential in this new scalar direction for some benchmark point. Okay, and now on the left you can see the region when the tunneling takes place. Okay, so you have, I don't know, 60 GeV, something like this. But then the true vacuum is much further, right? So we have many scales included in the problem. So one have to okay, one thing. So giving those corrections, like the formula is not that important, but the important thing is this mu here. This is the energy scale, the renormalisation group scale, right? And we have to pick something for it. So, but now when you look at this picture, you can't really have like a one safe choice. Like you can just say, oh, I'm going to put 60 or something, because now then at some point you are going to throw physics there, and it won't work. So what do you do? So we do the so-called renormalisation group improvement, and without going into the details, the mechanism behind it is that you put all of the couplings as a function of the scale, right? Okay, and also the field as well on this factor. So they depend on this key parameter. This key is this logarithm of this RG mu scale over some reference scale that we can choose. Okay, and in our case, we choose this mu to be the mass of this X boson. Okay, this is like a free parameter, and then we take the GX evaluated at this MX, and this is how we put this mu in type there. So we have running. As you can see, it's proportional to the fluid value, right? So everywhere we are, the scale is proportional to that place. Okay. Here, like here, we are the scale is proportional to this 40, there is proportional to 80, etc., etc. So it's working better. And of course, we have to put some cutoff in the IR, because at some point this GX grows really quickly. And our reference scale is the MZ boson mass. Okay, so
how do you choose the interactor?
it's taken by hand basically. There's not I mean there's one physical reason, but one just have to put it.
And that's insensitive to the way you choose this cutoff. The cutoff.
There is a sensitivity indeed to that, and it causes some numerical problem, I would say, and we chose this to like the lowest possible point for which we could calculate everything rather smoothly.
And the results are not dependent on the specific value you put. Yeah.
It's
so they change this by an order of magnitude. 1 dB the results don't change.
So it's changed on this way on this point where we can get the cutoff, right? Like so, we have this function, this dx is going like this. So if we are there, everything is perfectly safe. But yeah, we can't go there up to the 0, because then it goes the infinity, and it's very clear to like a catastrophe. So somewhere you have to stop. But then if you stop running, then all the other couplings also their scale dependence you have this something like this. So if you choose that point there, it will also change the result. Right? Like here it would be okay, but there the problem is okay. So that's one dependent. But on the other hand, when you are far away from the 0.1, it's working okay. That's not this point. Okay, so we have this RG improvement, and now what is our parameter space? So the nice thing about this conformal model is that actually you can have just a few or 3 parameters. So we have those 4, those lambda couplings and the new gauge coupling. But if you use Higgs, measure Higgs depth and Higgs mass and do some algebra, then after all, we can just be left with two parameters, and we chose those to be the Gx and the mass of this new X boson. Okay, and there we have several constraints. So here is the counter plot of a vec of this new scalar. Right, this is the log 10, so as you can see, it can go pretty big. And now the first region corresponds to a region where we don't have the correct electroweak minimum produced. Okay, so obviously, like this MX cannot be too aligned. The second region is, yeah, it's corresponding also to this situation. So if we have, let's say that this is GX over mu, and here we have this MZ, then we put this constraint here because in the calculation we have to go below this MZ, and then basically if it's but here it's bigger than this 1.15, if we chose it, then we get into this nasty region where everything grows rapidly. Also, the numerical calculations are basically doomed. And also, the last constraint for running couplings is also a situation where we don't have the electroweak minimum, because here at the MX scale, with the lambda 1 goes negative, so it's unbounded in the Higgs direction. Okay, so it's okay. So in the end, our potential in the model looks like this. We have these three level with running couplings and this contribution from boson, from X boson, and you may notice that there is no H, only this new scalar. And why is that? So this is the potential I was using for studying the phase transition. And the reason I could do this simplified version is this tunneling scenario in this model. So yeah, here this is the contour plot of the effective potential during the tunneling. So here you have the new scalar direction. Here you have the Higgs direction, and this is the true vacuum. And one would think that's okay, we just tunnel straight from the whole vacuum to the true one. But indeed, that is not what's happening in reality. We first tunnel in the phi direction and then roll down. Why is that? Well, you just calculate the action of your tunneling path, and you always get that it's more efficient for the field to do this instead of just going straight down. Okay, so that will allow us to work only with this during the phase transition with this simplified picture. Okay, so we have the model of the beyond standard model physics, right? So now we want to study the phase transition. So we want to include the temperature into the picture. So we implement thermal correction, and now we look how the thermal evolution of the potential look. So in the large temperatures, the symmetry is restored, and as the temperature grows, cools down. Okay. At some point, we hit the point where the two minima are degenerate, and we call this moment the critical temperature. Okay. Then we have the supercooling. So there's a lot of energy stored in the cold vacuum, and at some point, we hit a period of vacuum domination. If you look at this Hubble parameter, then yeah, we have those two contributions from the radiation and also the difference between the vacua. And at some point, we hit this temperature that from which this contribution starts to dominate. And this causes rapid expansion of the universe at this time. So the universe is expanding, and then at some point we have tunneling. And we define the nucleation temperature as the moment where we have one bubble per Hubble volume. Okay, so now the phase transition begins. We have bubbles everywhere. Okay, and then as they expand, at some point they percolate and gray transition completes. And here there are consequences of this vacuum domination period, because usually this from nucleation to percolation, it's really this thing happens really quickly, and you can more or less assume that those two are equal. However, now because we have this rapid expansion, bubbles need more time to meet each other. So as you can see, the temperatures are of the same order but still different, right? Okay, and also there is one thing. the question is, okay, but will they always meet each other? Will they always percolate? And no, it can happen that the space expands so fast that bubble will never collide and the phase transition never ends. And that will be another constraint on the parameter phase. Okay, and after that, we have we release this massive amount of energy, and we reheating the universe. And in our case, it's always instantaneous, so this vacuum energy transforms into radiation, and so the reheated temperature corresponds to this vacuum domination period. It is not always the case, but this is what happened in our model. People studied different version, for example, where you can have matter domination period and then you go back to radiation. Yes. Okay, so now I want to show some results for the model. So yeah.
So, is there any candidate in proto in one model?
One more time, sorry.
Is there any candidate in proto in your model? Which in your so is there any candidate some scale part which can play a role in proto?
Some candidate of Platon.
Which part can play a role?
I mean, it's not like a properly say inflation scale, more like a thermal inflation, and it's just caused by this vacuum domination of this new scalar field, this energy stored here in the vacuum. We don't have like I don't know, like a usual inflaton field. Yeah. Okay. So here are the results on the parameter scan on the model. And as you can see, we have two more constraints region, and I ask you to be patient. Next slide, I will tell what they are. So here you have the critical temperature, and there you have this vacuum domination temperature. They can grow very big, and they are above the electroweaks, let's say scales, right, above 100 usually. Okay, and then here are the plots for the nucleation and percolation temperature, and here is the reason of those two constrained regions. So we constrain this region because at some point we are hitting the temperature at which the QCD phase transition starts, and that complicates it. So for our analysis, we are not analyzing that. You can then it modifies your potential. You have additional mass-ish term from the quark condensate. However, yeah, for this work, we weren't getting into that region. And also, like I mentioned before, to have those region where the bubbles never meet, you check it in that way that you calculate the percolation temperature, and then you check if the volume of the false vacuum is shrinking. And here it doesn't. So it's not also. One can argue that, okay, but maybe at some point it starts shrinking, and what else? So it's kind of like an open question. It's not because right now this whole formulation applies to the cases where indeed at this TP the vacuum shrinks and it's okay. In that case, you don't really have more control over what is happening. Okay, so I mentioned the scale dependence, and now I also want to emphasize on that. So here are the same results, but for fixed scale. So here we are choosing the fixed scale on MX, right? So for these benchmark points, it's like 10 to the third, to the 3, etc. And here we put the scale for just the mass of the Z boson. As you can see, the parameter space changed dramatically. And also, this is important in terms of gravitational wave signal, a little bit smaller, but usually we have multiple sources of gravitational wave. And here, with RG improvement, we have those different sources. Here we just have one. So yeah, it's a, let's say, scale dependence is a single signal. Okay, so we know when the transition completes. At this TP, right? So now we have to compute all of the parameters necessary to get the gravitational wave spectra. So one of them is the strength of the transition, which is basically the energy difference between the minima divided by the radiation energy density. Then you have to have either the inverse time duration, or you can alternatively use the average bubble radius at the time the transition completes. And also there's an important parameter, which is the bubble velocity, and it's also the most difficult to compute. But this is a very strong transition. Okay, let's look at those values of alpha, which is and as you can see, those are very, very large. For example, in not regular electroweak transition, like for example, Mateusz here is studying the model, which is a standard model plus real singlet. Your alpha is of order 0.001, something ish like this. So this is way, way stronger transition, right? So here in our analysis, we are saying, okay, bubble is almost like expanding with the speed of light. And that's a very nice approximation. Okay, so yeah, that was the result for alpha. And then I said that we can choose one of those, either beta or the average bubble radius. So which one do we choose? Well, we choose the preterm, basically, because those two are actually proportional to each other. First is a factor in front. So as you can see there, the beta, it was a derivative. And then we have this interpolation here. This gamma is a probability of tunneling per volume. And it just looks uglier numerically. So we and R star is computed by integrating and stuff. So we just smooth it. So we are choosing this R star times R star in our analysis later. So this tells you basically how much horizon takes the value in average. So they can grow very large in the model, which is also not very common. Okay, then the next question. I know all the parameters, but then where do I get the gravitational waves from the phase transition? So we have a lot of energy in the bubble. Okay, now they start to expand, and now two things can happen. Either the bubble expands very, very fast, accelerates, and during this acceleration that they collide, then the gravitational waves are from the bubble wall collisions. The energy is stored in the walls, bubble walls mostly. However, if at some point the bubbles reach the terminal velocity, because you have the bubble, you have the plasma around it, and each particle going inside starts to becomes massive. So you have this effective pressure, let's say, friction, sorry. So if it reaches this terminal velocity at the moment of percolation, then the gravitational waves are sourced mostly by the sound waves in the plasma. Also, there's a third option, which is turbulences, but this is still a big matter of a big discussion in the community. So people don't really know how to. There are no like very detailed simulation that would tell us how to get the spectra. But the good news is that they are subdominant usually to those two. So we neglect them in the analysis. So we have bubble wall collision and sound waves in the plasma. And usually it's either this one or that one. But it is possible to have both in this model in particular. So here, this is the plot of the so-called efficiency factor for the sound waves. It basically tells you how much of your spectra is sourced by the sound, right? You can also have the efficiency factors for collisions. So if the kappa collision is 1, then everything is from collisions, etc. So yeah, this plot is for the sound waves. So here you can see that for the majority of the space, with the gravitational waves are sourced by the sound waves. There's a small space where we have bubble collisions, and in those plots with fixed scales, everything was sound waves. But also we have a small region where those two contribute more or less on the same order. Okay, so now we have everything. We can compute some spectra. And how do we do it? Well, you have to get the parameter that you just computed from the phase transition. You put them here. Then you get some from one of your colleagues some nice fits from the simulations. And here I'm citing two works by Marek Lewicki and Mile Vaskonen, who studied bubble collisions in extent, and also there is this nice summary of gravitational waves and phase transition in Caprini et al. Paper for Lisa. And the resolution is difficult, but anyway, here you have plots for chosen GX 0.76, and we change the mass. Okay, so this is from 10 to the 4 to 5.23-ish. And as you can see, as you change the mass, when the mass grows larger, the sound waves, which are the solid lines, sorry, turn into collisions. Okay, but nevertheless, it's still very nice visible in LISA detector. Also, we have the similar plot, but now we fix the mass for 100 TeV and change the coupling. And here, even better, you can see the change from the collisions to sound waves. And also here there is this one plot. It's kind of like double peaked. So this is the moment where those two contributions are of the same order. So that's why you have this double spectrum. Anyway, the signal is strong, is visible. The model is testable. I'm even going to argue more later. So
What is the instrument in the middle?
sorry,
What is that? LIGO? You have LISA, sorry? and then you have-
LISA, Edge, LIGO, and ET, Einstein telescope. Okay. Yeah. This is not the final result, but okay, we have the spectra. What else is there to come? So yeah, I promised that there is some dark matter analysis, and also in order to get the experimental prospect, you will have to compute signal to noise ratio. Okay, so those are the results for the dark matter in the model for this X boson. As you can see, it's we can achieve the correct relic abundance for rather small part of parameter space. Here we can have the constraint on the direct detection, and combining those two and getting the signal to noise ratio, we arrive at the final result. So those are the signal to noise ratio for LISA detector and for SNR. The rule is that if the SNR is bigger than 10, then you can detect the signal. Okay. And also this black line here corresponds to this part of parameter space where you can have the correct relic abundance of that matter with those X vector boson. And yeah, for LISA, basically for the whole of the parameter space, the model predicts a detectable strong signal. For Edge, it's more constrained. But also, if you want to include the dark matter, it's even more constrained, right? So you either have a lot of possibilities of detecting gravitational wave signal, or if you want to have this dark matter abundant, then it's well not so pretty. Okay, to sum up, I just want to emphasize 3 things. So if you have conformal models, then you have a generally strong gravitational wave signal in the phase transition. Then be careful for the scale dependence. You have to treat it somehow. Address the problem. And also, when you do that, your parameter space is highly constrained. And also, when you compute the percolation criterion, it's even more constrained, which gives you, in that case, also the dark matter parameter space. So the constraint. So that's all. Thank you.
Thanks very much for the seminar. And which question do we have for the speaker?
When you were looking at the parameter space, at some point you were saying that you were excluding some part of the parameter space because some coupling was becoming negative. You said
Lambda 1, this is
lambda 1, right? My question is, are you excluding this, I mean, from the beginning, or is a result of the analysis? The fact that it's becoming negative is not necessarily a problem. It's only a problem if you go there. But the fact that in the standard model, lambda, the pixel coupling is becoming negative, and still we are here. So,
okay,
so
but
having negative couplings is not a priori a problem. So we really explore that family.
so this is computed at 0 temperature, right? But we also end the phase transition at a really low temperature. So basically, this is also happening at the time transition completes. Like even when you reheat, okay, maybe the situation will change. The lambda 1 will go positive, but I mean, at least it will be bounded, but then you cool down and again, you unbound it.
Ahí está, no es problema, pero de luego,
Yeah, so I mean, this was before computing all of the phase transition stuff. Yeah, but it's a reasonable constraint, I would say.
another one is the self-coupling. And again, the scale which is becomes negative is which scale, which scale.
No, it becomes negative at the MX scale.
No soy trabajador de bueno, maybe. You have a matter, you have gravitational-wave, you have radiation.
No, okay, so that's of course you can have some baryogenesis with phase transition, but the usual picture requires rather slow walls. Here we don't really have slow walls, so people can try do it combined with leptogenesis, for example. There were some old paper on that, but then you also have to expand in the fermionic sector, etc. So here we don't touch the question of baryon asymmetry. But so I'm sure that's doable. Yeah, people are so creative with them.
Any other questions? Well, I myself, I have not heard about this edge experiment. Is there anything you could say about it? You know?
Okay, so
Sorry.
yeah, no worries, no worries. This is my excuse to think about it while I'm
Okay, good one, good one.
no, I overshoot. So this is, for all I know, the experiment suited both for gravitational waves and for dark matter detection, which is based on the cold atom physics. And
Okay.
also, it's one thing. So you may wonder why it ends here so well suddenly. It's because it's not well established how much on the left they will go. It's not like, yes, they have some, let's say, predictions, but like for just the safety of this analysis, because this region is more or less established, and then it's not yet well known how much on left in the lower frequencies they will be able to go.
Okay, but it's going to be an interferometer.
No, so
Okay.
it's really a power. I mean, they are like two versions. This edge, there is, I don't know which one is the biggest. Like it's a kind of American British collaboration, one is called edge and then one is minus. And it's a tower of taking this qualitative.
Okay. Okay, okay.
It's not really the usual.
Thank you.
There are only prototypes of 31 meter distance and some 1 kilometer and 1,000. I don't know how much.
Exciting time.
Indeed. So last call questions. Okay, everybody's very hungry. Okay, then yes, thank our speaker again then.
If you enjoyed the video, like and subscribe.